Hi, and welcome to a midterm review for Regents Chemistry class. Maybe you're just in high school chem, but in New York State, typically that's a Regents exam, the chemistry exam at the end of the year. But mid-year, we're looking at topics such as matter and energy, atomic structure, bonding. We may or may not have done nuclear at that point. So what we're doing here, this is part 2. Part 1, I'm going to go ahead and put a little link if you haven't checked that out. Those were all multiple choice questions that I went through related to the August 2024 Regents. That's the most recent Regents. And now we're going to take a look at the short answer questions. I have tons of videos and review on my channel, NY Chem Coach. I would advise you to check it out. The more you practice, the better off you're going to do. And with that, let's get started. So question 51, assuming that you've gotten to Lewis structures and bonding. If you didn't, then you wouldn't be up to this point. It asks you to draw a Lewis electron dot diagram for a molecule of ammonia. This is not a given question. If you don't remember the formula for ammonia, that's a problem. Now, there is a place on the reference table where you will find it if you don't remember it. So we're going to check that out. Here on reference table L, we see that aqueous ammonia, has the formula NH3. Now, that's a long shot. More than likely, you should memorize that ammonia is NH3, methane, for example, is CH4, water, hopefully you know, is H2O. Those are common molecules that we deal with a lot throughout the course. Now we got to draw a Lewis structure for NH3. The easiest way to handle Lewis structures when it comes to an exam is to memorize how these Lewis structures are made. You can reason it out, but there's not a lot you need to know. It's just a suggestion when it comes to the bonding unit. I'll show you, though, how to do it essentially from scratch. First thing to remember in bonding, we're always talking about the outermost electrons for an atom that are involved with an attraction for one atom to another, right? Those are the valence electrons. For nitrogen, we're talking about 5 valence electrons. And for hydrogen, we're talking 1. Now remember, we're talking NH3 here. We're doing a lot of talking. With the 5 electrons for nitrogen, if you know how to do the individual atoms' electron dots, it's going to make your life easier. The first 2 valence electrons are paired, and that has to do with what's known as a sublevel, which you may or may not have discussed in your class. Then from there, you have the next 3 electrons that we're building here in this outer level. They are going to occupy their own space or orbital, so we would go ahead and draw those as 3 separate dots. Right now, what I have is the dot diagram for nitrogen alone. But now I have these 3 hydrogen atoms. Well, each hydrogen atom has 1 valence electron or 1 dot. What I can do is I can go ahead and put a hydrogen here, a hydrogen here, and 1 here at the top, which may or may not work on my little board here. And now we have the electron dot diagram for ammonia. A pair of electrons represents a bond. Here, in this drawing for the Lewis structure, which is totally legit, instead of putting 2 dots for the bond, I'm using a dash. And then you see the lone pair of electrons on the top there for nitrogen. It doesn't matter what orientation you have, as long as you have the 3 nitrogen-hydrogen bonds and then the lone pair of electrons on nitrogen. Now, a couple other things you need to know about molecules besides drawing them, and that is the bonds, whether they're polar or nonpolar bonds, and the molecule, if the molecule is polar or nonpolar. When you have two different nonmetals, as you do here, you have what's known as a polar bond. And the reason being is nitrogen wants to pull the electrons closer to its nucleus versus hydrogen, which sets up what we call an asymmetrical or uneven distribution of charge. Now, also the shape of this shape is a pyramidal shape. You might think it looks like a T, but that would be two-dimensionally. Three-dimensionally, this lone pair takes up space, and it's a pyramidal shape. The pyramidal shape always means you have a polar molecule. The rest of the molecules that you need to know water, you need to know methane, you need to know the diatomic molecules as well. Carbon dioxide, those are the ones right off the top of my head. You need to know how to draw them. You need to know the bonding, and then whether or not the molecule is polar or nonpolar. With that, let's go to 52 and 53. For 52, it says, compare the energy of an electron in the first shell of a copper atom in the ground state to the energy of an electron in the second shell of the same atom. As you go further away from the nucleus of any atom, the electrons have more energy. It's just a fact, Jack. So when it says compare it, what we want to say is that the energy of the electron in the second shell is greater than the energy of an electron in the first shell. Now let's check out 53. Show a numerical setup for the calculating of the atomic mass of copper. Numerical setup means we are going to go and show the numbers, but we don't actually have to calculate the answer. Sometimes on these short answer questions, you do the setup. Sometimes you provide the answer. It just depends on the question. Here is the information we're going to use. There is no equation for the numerical setup in the back of the reference table. Reference table T has all of your equations, mathematical equations, but this one is not there. This question shows up all the time on the Regents, every single time. So that means you're going to see this a lot between now and when you take the exam, and of course the day you take the exam. Anyway, what we're dealing with is known as a weighted average. So let's go over that first. We see here for copper, these two isotopes of copper. Now, make sure you remember what an isotope is. Same number of protons, different number of neutrons. In nature, most of the time we're finding copper with a mass of rounded to 63. Then, almost a third of the time we see copper with a mass of 65. And the difference, of course, is just the number of neutrons. It's not 50-50. If it was 50% and 50%, I could just add them up and divide by 2. Since it's not, what we're going to do is we're going to get mad. We're going to multiply, we're going to add, and we're going to divide. Now, if you already know how to do this and you keep getting them correct, you don't have to do the mad way. But if you're still confused and having an issue, this might help. First thing is, what are we multiplying? Well, we're going to multiply the atomic masses and the natural abundance. I'm going to put it up here. So my atomic mass for copper is equal to, I got 62.93 times the 69.15. Okay, now I'm also going to go ahead and multiply the 64.93 times the 30.85. Now, here's the thing. The A means add. These are not multiplied together. They're added together. And we're going to divide. And what we're going to divide by would be 100. So multiply, add, divide. Here is our setup, and that is our answer. For questions 54 through 56, we are dealing with the periodic table, and in 54, identify the element in period 2 that is classified as a metalloid. A metalloid is another vocabulary word you should know. That means you have atoms of an element that have both metal and non-metal properties. Let's take a look at the periodic table and identify the element. All right, now period 2. You see the word period here. It means the rows. We're looking at period 2, and then we want to identify the metalloid. Hopefully you know this already. I call it the staircase, but this darker lines here as part of the boxes tell me that the elements sitting on what I call the staircase, and then germanium and antimony below, these 6 elements are considered metalloids. You don't necessarily have to memorize them. If you know the location, you're good. Remember, the left side of your table are your metals, and 2/3 of the table is comprised of metals, and then, of course, the right side is our nonmetals, including the noble gases, which are here in group 18. So our answer here is B, or boron. For 55, it says identify the element in period 2 that requires the least amount of energy to remove the most loosely held electrons from a mole of gaseous atoms of the element in the ground state. In other words, they're asking which has the lowest ionization energy. This is the definition for ionization energy. That's another vocabulary word that shows up a lot on the Regents exam. Now, let's go to the periodic table. Period 2, I've gone ahead and I've drawn the row so that you see it. And now, of course, we're looking for the lowest ionization energy. Ionization energies, along with a whole bunch of other parameters, are here on reference table S. Don't forget about this reference table. First of all, reference table S gives you names and symbols. A lot of times, the Regents exam will give you the name of something, and you might look it up on the periodic table. The periodic table doesn't have the names of the elements. You got to go to reference table S. In this case, we're looking for first ionization energy, and they made it easy for us because we don't have to go up and down the table so much, right? We're just going in order because it works out that way. And sure enough, lithium is the lowest value. Remember, your metals are your givers. Your nonmetals are your takers. So as I go across the table, if I go back, typically we're going from low ionization energies to higher ionization energies. That's the trend. But to make absolutely sure that you have the right answer, you can look up the numbers. All right, the last question here is about a trend. In this case, atomic radius. We're considering an order of increasing atomic number. That means from left to right. Let's go back. Once again, you might remember the overall trend, but it doesn't matter. You have it at your fingertips. It's known as reference table S. I go to reference table S, and now what am I doing? I'm looking at atomic radius, and look what's happening. In general, as the atomic number is getting bigger, the radius is getting smaller. All right, we are checking out here 57 through 59. 57 has to do with balancing. Typically, I would teach balancing in bonding and also types of reactions. Again, anything that you haven't gotten to since it's a midterm, then just go ahead and skip the video. In this case, we're trying to balance this equation using the smallest whole numbers. Always double check at the end after you balance that everything is the smallest whole numbers and you can't divide through and reduce everything. Well, real simple. Just move left to right. I have one lead on the left. I have one on the right. Because my my nitrate, NO3, stays intact, I'm going to go ahead and count that as one thing. I have 2 on the left, and I have 1 on the right. That would mean I needed 2 in front of KNO3. Now I go to Ki. Well, now my potassium is not balanced. I have 1 on the left and I have 2 on the right. I needed 2 in front of Ki. And then I go to iodine, 2I, and then I have an I with a 2. Now it is balanced. So it's going to be the 1 lead 2 nitrate, plus the 2 Ki goes to 1 PbI2 and then 2 KNO3. What is the chemical name for the aqueous product? The first thing you have to know is the AQ in parentheses. That is representing aqueous. And when you name a compound, it's just like the order of the formula. K, if you don't know that its name is potassium, you can look it up on reference table S. So I have potassium, and since now I have a metal and I have 2 nonmetals, I have a polyatomic ion. Don't get creative. This is not potassium, nitrogen, oxygen or something. No. I have to find the name of the poly. And if you don't recognize it as nitrate, which it is, this is potassium nitrate, of course, you can go to the reference tables and play the matching game. Let's do that. On reference table E are all the polyatomics and their charges. Now you're seeing charges here because remember, they're bonding with atoms, and therefore then they kind of even themselves out based on who's losing and who's gaining. Here is nitrate, and that's exactly what I needed. I don't change the name of anything. Just write it down exactly as you see it. For the last question here, I'm asked to determine the gram formula mass for the yellow solid compound produced in the reaction. By looking at the reading passage, I am told that the lead nitrate reacts with the potassium iodide in the test tube, that's here, produces a yellow solid that settles to the bottom. That has to be the PbI2. Why? Because the S stands for solid. When I go ahead and I teach gram formula mass, what I'm going to suggest, you list the elements as they appear in the formula, then the number of times they appear in the formula, which is once for lead, twice for iodine. You're going to pull the atomic masses off of the periodic table, multiply them out, and add them up. All right, so here it is. I got my 207 and then 2 times 127 for iodine at 254. My answer is 461. All right, 60 through 62. Now, 60 and 61 have to do with vapor pressures. That's when you have a liquid, when the molecules of that liquid go into the gas phase above the liquid. Not sure where your teacher is going to teach this, so you may be covering it now at the first half of the year, you may not. You're asked to go to table H And in question 60, identify the substance on table H with the weakest intermolecular forces. Let's do just that. We are here at reference table H, and we're looking at 4 substances: propanone, ethanol, water, and ethanoic acid. Over the entire temperature range, when I'm comparing these 4 liquids, the highest vapor pressure is always propanone. That means it has the weakest intermolecular forces. Conversely, ethanoic acid must have the strongest forces because throughout the entire temperature range, it has the lowest vapor pressure. You are asked which has the weakest at 40 degrees Celsius, so I went ahead and drew a line, and sure enough, the highest, again, is propanone. For 61, determine the vapor pressure of ethanoic acid at standard pressure and 50 degrees Celsius. Let's take a look. First of all, standard pressure is the dotted line. 101.3 kilopascals is standard pressure. It's actually on the front of the reference table if you forget, but that's why that dotted line is there. Then we were asked, it was 50 degrees. I come to the temperature line of 50, and I'm going to go ahead and it crosses ethanoic acid first, because it has the strongest intermolecular forces, and I go over. Now, every single one of the boxes here for vapor pressure go up by 10s, right? And how do I know that? I have 5 boxes to get to 50. So the first box is worth 10, but my ethanoic acid is below that line. Maybe I say 8 kPa, 8.5 kPa. On the answer key, teachers are given a range when it doesn't cross exactly perfect. So I'm going to go with my 8 kPa. For 62, explain in terms of charge distribution why water is a polar molecule. Well, it's the same whether it's water or any other polar molecule. We say that the charge distribution is asymmetrical. In other words, it's uneven. Water is polar, and polar molecules are asymmetrical. Your nonpolar molecules, which are your diatomic molecules, along with things like carbon dioxide and methane CH4, are symmetrical. So all I had to really say here is that the charge distribution is asymmetrical. An easy way to remember this is SNAP. S-N-A-P. Symmetrical, nonpolar molecules, asymmetric, polar molecules. You can tell I just skipped a whole bunch of questions, and the reason for that is they would be topics that you would cover the second half of the school year. I do want to address one question on here that may come up at midterm time, and that has to do with endo versus exothermic. Typically, if you've done any kind of energy unit so far with matter and energy, you're going to have to deal with endo and exo. So let's take a look. It says, state in terms of temperature why dissolving ammonium chloride, or NH4Cl, is classified as an endothermic process. If I go back and take a look, it says the temperature of the solution decreased as the ammonium chloride dissolved. All right, well, why did it decrease? Because the dissolving of the ammonium chloride is endothermic. And when you have an endothermic process, the temperature drops. Again, we're doing a little jumping here. We're going to skip 74, and we're going to check out on this page 75 and 77. For 75, it says, state what happens to potential energy of water molecules as they evaporate from a sample of seawater. In other words, we're going from the liquid phase to the gas phase. When you have molecules in the gas phase as compared to the liquid phase, they're more spread out. If you think about it, they have the more potential to interact with other things. Potential energy is increasing in this case. It's also, from a heating curve perspective, if you remember those, when you are at a plateau, which is a phase change. In this case, the second one would be liquid to gas. Temperature remains constant. That means kinetic energy is constant, but the potential energy is changing, and liquid to gas, it's increasing. For question 77, it says to draw at least 2 water molecules in a box showing the orientation of each water molecule towards a bromide ion. Now, I got to find the picture, and let's check it out. What you would see on your answer booklet or in your answer booklet is the bromide ion. It's negatively charged. It has the minus sign. And now your water molecule, you have a big circle that represents oxygen, and then the 2 filled in circles smaller, which represent hydrogen, right? Water is H2O. Well, water, remember, is polar, asymmetrical. Oxygen's more electronegative. It's pulling the electrons closer to the oxygen end and makes the 2 hydrogens the positive end. When I draw at least 2 water molecules, what that means is I want to be very deliberate here and make sure the positive end of my water molecules, wherever I put them, are pointing towards the bromide ion. I guess I should draw this a little closer, right? Like that. So just follow that key and make sure you orientate them and draw at least 2. All right, these last 4 questions have to do with nuclear chemistry. Now, if your teacher didn't get to nuclear yet, obviously you're done with the short answer review here with the August 2024 Regents Exam questions. If your teacher did include this, then let's go over these together. No matter what, check out all the videos I have on my channel. There's a lot there. There's a lot of old Regents exams with the answers explained. If you could do me a favor and subscribe, this way when I add new videos, you'll get notification. But no matter what, keep working hard. Good luck. And with that, let's go to 82. It says state the neutron to proton ratio in the helium product of the reaction. That's a weird way to ask a question here. All they're asking you is your neutrons, 4 minus 2 is 2 neutrons, and of course your atomic number is your element's social security number, 2 protons. If you change the number of protons, remember that changes the identity of the element. So what's my ratio here? It's 2 to 2 or 1 to 1. That was the ratio. Okay. For 83, based on reference table N, state the decay mode of tritium. Now, tritium, you see it here. Let's check out reference table N. They're kind of trying to confuse you. Again, hydrogen 3 is tritium. Notice that they give you the mass number. Of course, the atomic number is always 1, but the word isn't here. They have it as hydrogen 3, so I could see a student getting confused. Decay mode, here it is. It's beta minus decay, or I'm sure you could even put the symbol with the minus sign and get credit. Question 84. This, just like the atomic mass question, always shows up on the Regents exam. Depending on how you're taught by your teacher, there's more than one way to handle the half-life problems. Whatever works for you works for me. It says determine the time required for 1 gram sample of my tritium produced to decay until 0.25 grams remains unchanged. For this, let's do a table. We have mass and we have time. Again, you're not going to find any type of mathematical equation on reference table T. I started with 1 gram of the sample, and that was at time 0. Then what happens is when I have half a gram left, whether I put it as 1/2 or 0.5, now a half-life has gone by. A half of a half, now a quarter or 0.25, and that'll be another half-life. So what we need is we need the half-life for tritium or hydrogen 3, and then we need to go ahead and multiply it by 2. Here it is, 12.31 years. I'm just going to go ahead and add it up twice. I double-checked the answer key. Doesn't matter with sig fig, so 24 is the answer, or it's going to be 24.62 years. All right, the final question is going ahead and figuring out what's missing for this nuclear equation here in the answer booklet. Remember, when you're balancing nuclear equations, the numbers on top, the mass numbers, have to be equal on both sides of the equation, and the atomic numbers, the lower numbers, have to be equal on both sides of the equation. I'm starting on the right-hand side because I have my tritium and my helium. 3 plus 4 is a total of 7. I have 1 for the neutron on the left. What number plus 1 equals 7? Well, that's going to be 6. Then on the right, I have 1 plus 2. That equals 3. On the right. And then on the left, I have a neutron, which is 0. What number plus 0 equals 3? That's 3. All I need to do now is identify element number 3 from the periodic table, which is lithium. And there is my answer. But you have to have the 6 for sure. Okay, so again, it's what number plus 1 equals 7. That was 6. And what number plus 0 equals 3 is 3. With that, we are done with this review. I hope that it helped. And again, keep working hard and good luck.